In this lesson, we will learn how to identify aqueous negative ions based on their reactivity and the colour and solubility of their salts. In the laboratory, it's useful to know if we have substances that are dissolved in a sample of liquid water or not. In other words, whether the sample of water is pure. It may also be very useful to be able to identify which substances are present in an unknown solution. Many substances dissolve in water. In this lesson, we will focus on substances called ionic salts. Many ionic salts dissolve easily in water to make solutions. Ionic salts that dissolve easily in water are therefore known as soluble salts. If we added a soluble ionic salt to water and stirred well, we'd expect to get a solution of the ionic salt. Once the ionic salt is dissolved, we would not be able to tell that the salt particles are in the solution. Very often, ionic salts have no obvious colour. This is particularly true for salts of metals from Group 1 and Group 2 of the periodic table. Many ionic salts also have no obvious smell, and when they dissolve in small amounts to make solutions, it seems that they have disappeared. However, ionic salts contain positive ions and negative ions held together by strong ionic bonding in a crystal lattice. The positive ions are known as cations and the negative ions are known as anions. In the case of the salt sodium chloride, the cations are sodium ions or Na+, and the anions are chloride ions or Cl-. When these solid ionic crystals are placed into water, the ions are surrounded by water molecules and they break free from the crystal lattice. The ions become dissolved into a solution where they can move around freely. So solutions of ionic salts will contain cations and anions that are mobile in the solution. Very often we wouldn't know that they're there just by looking at the solution. A sodium chloride solution will contain positively charged sodium ions and negatively charged chloride ions. Both ions are colourless, so a solution of sodium chloride looks just like a sample of pure water. In the laboratory, it may be very important to know if these ions are present. We must assume that all unknown substances in the lab are toxic or poisonous, so we must never taste unknown samples. We need some simple chemical tests to answer questions such as, are there chloride ions in this solution? Fortunately, there are a range of reliable tests that can easily be performed in a lab with some test tubes and some known test chemicals or reagents. These tests are quick and give an obvious result. Simple observations that may be noted during these tests might include colour changes. This includes turning colourless. Another observation we may notice is the appearance of a solid from a mixture of solutions. This is known as a precipitate. We might notice gas bubbles or fizzing, which is also known as effervescence, being produced from the reaction mixture. The observations need to be unique for the ions being tested, so that the result does not cause confusion. It would not be a reliable test if several different ions all produce the same result in a chemical test. In this lesson, we're focusing on tests for anions or negatively charged ions. We will see how the tests for chloride, bromide and iodide ions, collectively known as the halide ions, are performed. We will also see the tests for sulfate and sulfite ions. These are distinctly separate ions, despite their similar names and chemical formulae. We will also see the test for carbonate and nitrate ions. We will see which observations would be noted to confirm a positive test result for these ions. We will begin with a chemical test for carbonate ions. Carbonate ions are an example of a base. If they are present in a solution, they will react with acids to produce carbon dioxide gas. For example, sodium carbonate is a soluble metal carbonate. When it's dissolved into water, it will release carbonate ions into the aqueous solution. When we add hydrochloric acid to sodium carbonate, the salt sodium chloride and water and carbon dioxide are produced. This is a neutralization reaction. So if we add a few drops of dilute hydrochloric acid to the carbonate solution, bubbles of carbon dioxide gas will be observed. This observation may also be described as fizzing or effervescence. We cannot see the carbon dioxide produced as it's colourless. It's also odourless. The observation in this test is the fizzing. Of course, many other gases may cause fizzing, so to prove that the gas is carbon dioxide and that it originated from the carbonate ions, we bubble some of the gas through a lime water solution. This may be done by collecting some of the invisible gas from above the liquid in the test tube with a plastic pipette. The air is squeezed out of the pipette first and filled with carbon dioxide gas only. It is transferred immediately to the lime water in a separate test tube and bubbled through it. Alternatively, if a lot of gas is produced, a delivery tube may be used to bubble the gas across from a reaction vessel. Lime water contains calcium hydroxide. Lime water reacts with carbon dioxide gas to produce a white milky precipitate. This precipitate is calcium carbonate, which is very insoluble. This additional step to the test confirms that the gas is carbon dioxide and that the original solution therefore contained carbonate ions. Halide ions are found in salts containing the negatively charged ions of the halogens. Although halogens may produce coloured solutions in water, the halide ions are all colourless. To test for halide ions, we must first acidify the test solution with dilute nitric acid. This step is done first to remove other ions that may be present, such as carbonate ions and hydroxide ions. If present, these ions will give a positive result in the second part of the test, which would be misleading. It's important to use nitric acid here and not hydrochloric acid, as hydrochloric acid contains chloride ions. We don't want to add the ions that we're actually testing for. After the addition of a few drops of dilute nitric acid, a few drops of silver nitrate solution is added. This is usually stored as a dilute solution in a brown bottle as it's light sensitive. If halide ions are present, some solids will appear from the solutions. These solids are called precipitates and they have distinct colours. Chloride ions will form silver chloride, which is an insoluble white precipitate. Aqueous silver ions react with aqueous chloride ions to give silver chloride, which is a white solid. Bromide ions will form silver bromide, which is a cream-coloured precipitate. Aqueous silver ions react with aqueous bromide ions to produce solid silver bromide. Iodide ions will form a yellow precipitate of silver iodide. Aqueous silver ions react with aqueous iodide ions to give silver iodide, which is a solid. Note that fluoride ions cannot be identified using this test, as silver fluoride is soluble and does not produce an observable precipitate at all. The white, cream and yellow precipitates formed in these tests can be hard to distinguish from each other on occasions. For example, silver chloride can darken on exposure to light. A further test using ammonia solution can be used to confirm which silver halide is causing the observed precipitate. Silver chloride dissolves easily if some dilute ammonia is added to the precipitate. Silver bromide only dissolves in concentrated ammonia solution. Silver iodide is insoluble in dilute and concentrated ammonia solutions. If solid halide salts are available, concentrated sulfuric acid may be added to a small quantity of the solid salt to produce interesting observations. As the likely products of these reactions are harmful or toxic, these tests should be done in a fume cupboard. If we took 4 test tubes containing solid samples of sodium fluoride, sodium chloride, sodium bromide and sodium iodide and added a few drops of concentrated sulfuric acid to each tube in turn, we would expect the following observations. Upon warming slightly, the sodium fluoride will produce corrosive fumes of hydrogen fluoride gas. This will etch the glass on a glass rod with a drop of water on the end of it. The sodium chloride will produce acidic fumes of hydrogen chloride gas. These fumes will appear as steamy white fumes. This gas will turn damp blue litmus to red. The sodium bromide will produce orange fumes of bromine and also sulfur dioxide gas, which is an acidic gas. Sulfur dioxide gas will turn fresh acidified potassium dichromate paper from an orange to a green colour. The sodium iodide will produce a range of products. Most noticeable are a purple vapour caused by iodine and a smell of rotten eggs caused by the hydrogen sulfide gas. The iodine may condense as a brown or black solid inside the mouth of the tube. Sulfate ions in solutions can be identified using a combination of hydrochloric acid added first, followed by barium chloride solution. The acidification step is needed first to remove other ions, such as carbonate ions, that will interfere with the test by giving a false positive result. Any carbonate ions are removed as carbon dioxide gas. After acidification with hydrochloric acid, not sulfuric as this contains sulfate ions which we're testing for, a few drops of barium chloride are added. Barium chloride is a very soluble barium salt. If sulfate ions are present, a dense white precipitate will be produced. The precipitate is barium sulfate, which is a very insoluble barium salt. Barium sulfate is so insoluble it can be used in medical applications where it is swallowed to provide contrast on X-ray images. It does not poison the patient as it is not absorbed into the body. The reaction occurring in this test is often represented by the simplified ionic equation, where spectator ions have been removed. Aqueous barium ions react with aqueous sulfate ions to produce barium sulfate, which is a white solid. Sulfite ions have the chemical formula SO3 2-. The word sulfite is sometimes spelled with a P and an H instead of an F. The sulfite ion is also sometimes known as the sulfate 1V or sulfate 4 ion. This is easily confused with the sulfate or sulfate 6 ion, which has the formula SO4 2-. Sulfite salts and sulfite solutions are less commonly encountered in the laboratory. They're sometimes used as preservatives in food products. There is an interesting test to see if they are present in solution. When hydrochloric acid is added to a solution containing sulfites, sulfur dioxide gas is produced. Although sulfur dioxide gas is very soluble in water, its presence can be confirmed by using fresh acidified potassium dichromate paper. The damp paper will turn from an orange colour to a green colour. Alternatively, a drop of potassium permanganate solution, acidified with sulfuric acid, may be held in the gas using the tip of a glass rod. The purple solution, containing manganate 7 ions, will become colourless as manganese 2 sulfate is produced. The presence of nitrate ions in a solution can be confirmed by adding sodium hydroxide solution first. Then, small pieces of aluminum foil or aluminum powder are added. The mixture is then heated carefully and ammonia gas will be produced. The ammonia gas can easily be detected by placing a piece of damp red litmus paper above the mouth of the test tube. It will immediately turn a blue colour as ammonia gas is less dense than air. The presence of ammonia gas generated in this reaction proves that nitrate ions were present in the original solution. As all common nitrate salts are soluble, it's not possible to use a simple test forming a precipitate for the nitrate ion. We will now look at a question to test your understanding of testing for anions. What is the net ionic equation for the reaction between barium nitrate and a metal sulfate, which is used as a test for the sulfate anion? A NO3 aqueous plus SO4 aqueous gives SO3 aqueous plus NO2 gas plus O2 gas. B Ba solid plus SO4 aqueous gives BaSO4 solid. C Ba2 aqueous plus SO4 aqueous gives BaSO4 solid. D Ba2 aqueous plus SO4 aqueous gives SO2 gas plus O2 gas plus Ba solid. E BaNO3 solid plus H2SO4 aqueous gives BaSO4 solid plus 2HNO3 aqueous. In this question, we need to consider the reaction between barium nitrate, which is a soluble barium salt, and a metal sulfate, which can be represented as MSO4 AQ, since it also must be soluble. Since we are going to show a net ionic equation for this reaction, only the ions reacting will be shown, any spectator ions will be removed. Spectator ions are those that do not change in the reaction at all. When 1 mole of barium nitrate is dissolved in water, it yields 1 mole of barium 2 ions and 2 moles of nitrate ions. These are aqueous ions. When our soluble metal sulfate, represented as MSO4, is added to water, it will yield 1 mole of M2 ions, aqueous, and 1 mole of SO4 ions, also aqueous. Now we have a complete list of reactant ions, we can consider what happens to them during the course of this reaction. The barium ions react with the sulfate ions to form insoluble barium sulfate. This is written BaSO4 The metal ions and nitrate ions form a soluble nitrate salt. As these ions are soluble, they can be added to the list of products in our ionic equation. The nitrate ions and metal ions are in fact spectator ions, and they can be removed from this ionic equation. This produces the net ionic equation, which exactly matches answer C with the correct state symbols. Now we can summarise the key points in this lesson. Carbonate ions react with acids to produce carbon dioxide gas, which turns lime water milky. Halide ions react with silver nitrate solution to give silver halide precipitates that can be identified from their colours. Sulfate ions react with soluble barium salts to give a white precipitate of barium sulfate.